So yeah, first slide. Yeah. So first, we're going to talk about data privacy. So in our data privacy side, we suggest using encryption, particularly AES-256, which is one of the most widely used encryption techniques, and it ensures that data is scrambled into an unrecognizable form, making it nearly impossible for unauthorized parties to interpret the information without the decryption key. So we suggested this because AES-256 refers to an encryption key that is widely used in high-level security. It's used by governments, financial institutions, and healthcare providers as well. It's actually part of the U.S. Global Encryption Standard, and it's mandated by regulations like the HIPAA for securing sensitive healthcare information. So this is possible with the use cases. Particularly, this affects data in transit and data at rest. Firstly, it has data in transit by protecting data as it moves from one location to another, such as from a patient's device to a hospital server or between cloud storage systems. And even if it's intercepted, encrypted data would be unreadable. Second, data at rest. This ensures that the stored data remains secure and inaccessible without the decryption key, and it prevents hackers from accessing sensitive information even if they infiltrate the storage system. And according to the Ponem Institute's 2020 Cost of a Data Breach report, companies that implement encryption techniques like AES-256 reduce the average cost of a data breach by $360,000. And hopefully, in the event of a breach, the encrypted data cannot be readily used, which will minimize potential financial losses, reputational damages, and regulatory fines possible by the General Data Protection Regulation. So moving on. So ways to obtain informed consent from patients from AI algorithms. Firstly, our first method is to use simplified consent forms, which uses clear and easy to understand languages to explain to patients how their data will be used by AI systems. This matters because a lot of complex consent forms, often filled with technical jargon, can prevent patients from fully understanding the implications of what consent means. And simplifying the language ensures that the patients are more aware how their data will be handled. So we will do this through layered consent particularly. And this layered consent provides information to patients in multiple stages or layers. So initially, patients are shown a high-level summary that provides an overview of the key points. Then patients can then choose to dive deeper into more detailed explanations if they want more specific information. Hopefully, this is designed to avoid overwhelming patients with too much information at once. And research by the European Data Protection Supervisor shows that layered consent forms improve user engagement and understanding by 60% compared to standard one-size-fits-all AI consent forms. Hopefully, leading to better decision making about whether to provide consent for patients. So moving on. So lastly, we're going to talk about also the practices for data anonymization and secure data storage. Particularly, we want to use the differential privacy technique, which is designed to ensure that individual data points within a dataset cannot be re-identified, even when data is used for analysis or shared. It works by adding noise or random data to the dataset, making it impossible to link back the results to specific individuals, which still allowing them for useful statistical analysis. And Google and Apple were pioneers of this method. And according to the 2021 Privacy Practices Report, this has shown to reduce the risk of privacy breaches by over 90%, ensuring that sensitive information remains anonymized even when aggregated data is used. Thank you.
Presenting the algorithm bias. In this proposal, we present a technical four-stage plan to identify and mitigate bias in Metasys AI algorithm systematically. Data auditing is the first step in mitigating bias. We'll thoroughly analyze the training data for demographic imbalance, focusing on age, gender, and race to ensure all groups are adequately represented. Next, we'll implement a bias testing framework using Google's Fairness Indicator API. This allows us to test models' performance across different various demographic sizes and see how changes in the data affect model decisions using tools like Google What If tool. Finally, performance evaluation will follow the MIT bias testing standards, measuring model across four criteria: demographic, parity, equal opportunity, false positive rate, and calibration. This ensures consistent, fair performance across all groups. Mitigating bias. Moving to the next step, we have three key components in the next step: pre-processing, in-processing, and post-processing. Pre-processing is crucial for addressing data imbalance. We'll apply synthetic binary oversampling technique called SMOT to create synthetic samples of underrepresented groups, ensuring that the dataset is balanced, and this technique reduces the risk of AI overfitting to majority populations and improve accuracy across all demographics. During in-processing, we'll embed fairness constants directly into the model's loss function, ensuring that the algorithm doesn't disproportionately favor one group. For instance, we'll apply techniques like demographic parity or equal opportunity across different groups. Adversarial debiasing will also be used to actively penalize the model if it learns discriminative patterns. In post-processing, we'll fine-tune prediction thresholds for each demographic to balance true positive and false negative rates, ensuring consistent accuracy across all groups. Additionally, for cases where the model's confidence is low, especially for underrepresented groups, we'll use confidence-based deferral to defer these decisions to human experts, minimizing potential harm for uncertain predictions. Last but not least, after building the AI, continuous monitoring and governance are as equally as important. To ensure fairness in real time, we'll implement YLab, Tech AI, or HIAB, etc. Continuous monitoring tool that tracks key metrics like demographic parity. It will flag any disparities as new data flows into the system, ensuring immediate detection of potential bias. Additionally, we'll regularly retrain the model using new diverse data to prevent bias from re-entering the system over time. On the governance side, we'll establish an ethical review board to audit algorithm fairness and ensure compliance with regulations such as HIPAA and GDPR. For HIPAA compliance, will ensure strict privacy by data anonymization, removing all identifiable information before training and assigning each case a special time key encryption, using end-to-end encryption for all stored and transferred data with access limited to authorized personnel only. De-identification standards, following HIPAA's safe harbor method, ensuring none of the 18 HIPAA identifiers represent data use agreements, DUA, will establish clear DUA with healthcare providers, ensuring only essential data is shared and used for model training adhering to HIPAA's minimum necessary standards. These 4 steps are concluded. Holistic plan for a meta-assist AI still safety while still following standard regulations requirement for HIPAA and GDPR. Thank you.
And lastly, we will talk about transparency and accountability. And I will point out 3 main challenges in transparency and accountability. So the first challenge is complexity and interpretability. So Meta-assist machine learning algorithms for medical image diagnosis are likely to be complex. So it makes it difficult to explain their decision-making process in simple, understandable terms for all stakeholders, especially the patients who do not have the clinical knowledge. And the next challenge is the black box problem, which leads to trust issues among stakeholders. So many AI systems, especially deep learning models, operate as black boxes, where even developers may not fully understand how specific decisions are made, and therefore healthcare providers may be reluctant to fully trust these AI-driven diagnoses and might reluctant to integrate AI suggestions into their clinical decision-making without transparent explanations. And it is even harder to build trust within patients, the people who are directly affected should the AI model not work as expected. Pew Research Center has pointed out that 60% of Americans would be uncomfortable with providers relying on AI in their own healthcare. And the last challenge is accountability. So it is really hard to establish clear accountability because AI systems involve many stakeholders, from data scientists and developers to healthcare practitioners. So it can be unclear who is responsible if something goes wrong. And from that, we'll have some recommendations that Meta-assist can provide. So the first recommendation is to implement explainable AI techniques to address the black box problem and improve transparency. So explainable AI are machine learning algorithms for understanding and interpreting decisions made by systems. So explainable AI techniques like LAM, which is local interpretable model agnostic explanations, provides a generic framework to uncover these black boxes, as you can see in the picture. These methods can provide interpretable case-specific explanations by highlighting the key factors influencing each diagnosis. Like, for example, the system could use heat maps or featured importance graphs to visualize areas of medical images that contributed most to a diagnosis. The next solution is to establish an AI ethics board, which involve all of the parties, AI owners, developers, and users, to patient representatives. And this board would oversee the development, deployment, and auditing of Meta-assist, ensuring the ethical standards are maintained, and regular audits as part of this governance structure can ensure ongoing transparency and identify potential biases or risks. And the final recommendation is to implement a tiered transparency approach. So health tech solutions will provide different levels of explanation tailored to various stakeholders instead of one-fit-all approach. So, for example, for regulatory bodies and healthcare institutions, a detailed technical explanation might be needed for them to fully understand the system. And for healthcare professionals who already have the technical knowledge, then simplified visual explanations might be helpful for them to better understand the diagnosis made by AI. And then for patients, then easy to understand summaries might be a better approach. And that is our proposal for Meta-assist.
The recording.